I am Alexander, and this is the presentation of CBGL, a fast Monte Carlo method for solving the global localization problem with a 2D LiDAR sensor in a 2D map. The gist of this presentation is that if you have a 2D LiDAR placed in any environment, the environment's map, and a single sensor measurement, CBGL may estimate the position and orientation of the sensor in the map without prior information in roughly 1 second per 100 meters squared of environment area, while at the same time being robust to varying maximum sensor ranges, its field of view, input noise, and repetitions of map portions. In the global localization problem, we want to estimate the 3 degree of freedom pose of a sensor in a map of the environment it is placed in without having any other information except for the map itself and measurements from the sensor. You can imagine the problem as if you were a robot and you just opened up robotic Google Maps but without the satellites. You must first know what your location and orientation are in the space you are navigating in for any subsequent autonomous navigation to occur, and this is what makes solving this problem important. The global localization problem is one of the 3 main localization problems in mobile robotics, the other 2 being pose tracking, equivalent to Google Maps tracking the pose of your cell phone as it moves, and the kidnapped robot problem. A solution to global localization is necessary and crucial for robots relying on observer-based localization methods, that is, methods that determine the pose of a robot only from measurements derived from onboard sensors. This concerns much of indoor situations where GPS is denied or where costly motion capture infrastructure cannot be utilized. The contributions of CBGL are 1. That it solves the problem faster than any other Monte Carlo method. This is because it is based on the cumulative absolute error per ray metric, which is computable in ON time, where n is the number of rays of the LiDAR sensor. 2. That it yields a higher discovery rate than state-of-the-art methods that solve the same problem. But these 2 are just side effects. The pièce de résistance is that CBGL extends from the pose tracking problem to the global localization one and validates that, given a dense enough pose hypothesis set, the cumulative absolute error per ray metric is able to estimate pose estimate error hierarchies solely by using one LiDAR measurement of the map. This is important because while the pose error of a single pose hypothesis is fundamentally unknowable, if we disperse enough pose hypotheses over the map, calculate their KR metric, and rank them by this value, the top of this hierarchy will include hypotheses in the neighborhood of the sensor's pose. Before moving on to the details of CBGL, we must first have to visit some concepts from the method's background. The first one is the concept of the map scan. A map scan is to the map of the environment exactly what a measurement from a LiDAR is to the environment itself. If you had a flawless sensor and a flawless map, a map scan from an estimate of the sensor's pose with 0 pose error would report the same ranges as the physical sensor's measurements. The second one is the concept of scan to map scan matching, or SM2. Just like scan matching gives us the transform between 2 real range measurements, scan to map scan matching gives us the transform between a map scan and a real scan. This is important for localization because if we have a pose estimate in a neighborhood of the sensor, this transform essentially provides the pose of the physical sensor itself, which is what we seek after all. The third concept is that of the cumulative absolute error per ray metric. The definition of the metric itself is very simple, as you can see from this formula. We simply subtract the ranges of a virtual scan from those of a real scan element-wise, take their absolute values, and sum them. The power of the metric is revealed when we use it between one real scan SR and a multitude of virtual scans SV, which have been captured within the map from pose estimates in a neighborhood of the sensor's pose. What is generally true in this case is that the KR metric is proportional to a pose estimate's position error and also proportional to its orientation error, meaning that estimates closer to the sensor's pose report smaller KR values than those farther away from it. We can exploit this fact for producing LiDAR odometry via plane scan matching, or for improving the pose estimate of localization during pose tracking. The question is what happens if we zoom out of that neighborhood. If the same pattern holds for neighborhoods of arbitrary radius, then we may localize the sensor by dispersing a dense cloud of pose hypotheses on the map, calculate their KR values, and pick the one that scores the minimum. In reality, what happens is that generally, outside of this neighborhood, the metric's values are larger than inside of it, and the metric is not disproportional to these estimate errors. These are still sufficient conditions for a solution resting on this metric to be able to localize a sensor accurately and in minimal time. This is the motivation that led to the inception of the CAIR-based Global Localization Method, aka CBGL. CBGL first disperses a number of hypotheses on the map of the sensor's environment. This number is a function of the map's traversable area. Then, in algorithm 2, it computes the CAIR value of each hypothesis and ranks them ascendingly. Subsequently, it selects a number of the bottommost hypotheses and it matches the virtual scans captured from them against the sensor scan. This act helps obtain lower error estimates, helps by diverging false positive estimates, and disengages the output from the input position and orientation density. In the end, CBGL calculates the CAIR values of the outputs of this process and selects the one with a minimum value. In order to determine CBGL's performance and the limits of its reach, we performed a number of tests. The first type of test is an experiment in real conditions in the CSAL lab of the Aristotle University's Department of Electrical and Computer Engineering with a Hokuyo LiDAR of maximum range of 30 meters and an angular range of 270 degrees. In this figure, you can see the trajectory that the sensor followed in the map, along which it captured over 6,000 range measurements. Each of these measurements we fed into CBGL, along with the map that you just saw, and 99.1% of its outputs came out to have a location error less than half a meter, and more than 94% of them have orientation errors less than 4 degrees. The mean execution time in this environment, whose area is 180 square meters, was 1.6 seconds. The next type of test was in simulation, where we can construct any type of environment we want and with any sensor properties in order to stress test the method with regard to these variables. Here we consider a cheap sensor, meaning with considerable noise, and we limit the maximum range of the sensor to 10 meters. The first environment is a warehouse larger than 700 meters squared in area, with large empty spaces, where the method is tested against missing measurements and therefore increased ambiguities between pose hypotheses. The second environment is a large office complex around 2,000 square meters in area, whose purpose is to test the method against similar surroundings and therefore give us an idea of the method's ability to make fine distinctions between them. We place the sensor in 16 challenging poses and call CBGL 100 times for each. As you see in both cases, the median position error was less than 15 centimeters, the orientation error less than 10 degrees, and 9 in 10 outputs or more exhibited a position error less than half a meter, with the execution time being less than 10 seconds in both cases. The last type of test we conduct in order to get a sense of how different angular ranges and different scan to map scan matching methods affect the output and what the profile of the execution time is with respect to map area. The experimental procedure was conducted in over 45,000 simulated environments, over 2 angular ranges, and 4 different SM2 methods. And these show that the core of CBGL, that is CBGL minus the SM2 method, is robust to varying angular range, and that execution time is roughly 1 second per 100 meters squared of area at 1 ray per degree. Where CBGL fails to perform so well is when the sensor is situated in or very near door thresholds, or when the number of poses selected for matching is too small when the sensor is placed in ambiguous surroundings. Thank you very much for your attention and for your time.